Hello everyone, welcome to my calculus lecture. So in this lecture, we continue to discuss the first and the second derivative test. Particularly in this lecture, we're going to talk about the second derivative test. So before that, we begin with the notion of concavity. Okay, so here comes the definition. If the graph of f lies above all its tangents on an open interval I, it is called concave upward on I. If the graph of f lies below all of its tangents on I, it is called concave downward on I. Okay, so what does this mean? When you study like a new, so definitions of like new concept and so on and so forth, right? Okay, it is always good to use a simple example. Draw a picture and try to visualize it, like what the concept is telling you about, and actually it really does help you understand the new notion better. Okay, so here the what actually we talk about concave up, concave down is the following. So the concave up, locally the shape of your graph is gonna look like this. So sort of like the smiley face. Okay, all right. And so in this case, if you draw tangent lines, okay, right, are going to be lying below the graph, all right? So that's what it said. So, when you look at this kind of a simple picture, you can easily understand, right? So concave upward case, right? Concave upward case, the graph lies above all its tangent, right? On an open interval. On an open interval means, locally, right? The shape is gonna be like this, okay? Likewise, concave downward case, actually, locally it looks like a frowning face, okay? Right. So, if you draw tangent line, oh, that was wrong. Okay. So, the graph of f actually lies, the below the tangent or the tangent. Okay. Right. So, we see that the definition makes sense. All right. And here comes another definition. A point df of d. So you see that in this case, this is not just the x point, but point on the graph. Okay, point on the graph, right? Of y equals f of x is called a point of inflection, or simply inflection point. An inflection point if the concavity of the graph of f changes from, right, smile to frown, concave upward to concave downward, or from concave down to concave up at this point. Okay, so the compared with the critical point case, actually critical points are only like the x coordinates, right? X points, right, but the at the critical point, the state of your function changes from increasing to decreasing or decreasing to increasing. And at the inflection point, the concavity of the graph changes from concave up to concave down or concave down to concave up. Okay? And the candidates for the point of inflection may be found by solving the equation f double prime of x equals 0. Why is that? You're going to see that in a moment. Okay? Because while the state of function, like whether it is increasing or decreasing, can be determined by f prime of x, the concavity is closely related to the second order derivative f double prime of x. So f double prime of x determines whether the graph is concave up or concave down on an open interval. So here comes the concavity test. Okay, so what the theorem says is if f double prime of x is positive for all x in an open interval I, the graph of f is concave up. Okay, on that interval I. If f double prime of x is negative for all x in an open interval I, the graph of f is concave down on that interval I. And why is that? The picture, simple picture I showed you earlier, right? That actually explains also. So as you can see, in this case, that's concave up, right? So let's see what happens to the slope of, not the slope, sorry, what happens to the slope of, the tangent line. So as you can see, in this case, the slope of tangent line is increasing, okay? In fact, these two are negative slopes, right? Negative slopes. But actually, this slope is greater than this slope because, they have negative slopes. And then, slope becomes 0 as x increases, right? And then the slope turns into positive, and actually it keeps increasing. So f prime of x is increasing in this case. Okay, let me write that down. So in this case, you can easily see f prime of x is increasing, which means that, right, that's equivalent to saying f double prime of x is positive. So here I applied what? Increasing, decreasing test, increasing, decreasing test. Okay, so that's equivalent to saying f double prime of x is positive. Okay, and similarly here, when you have like locally, when the graph is concave down, as you can clearly see, the f prime of x, okay, in this case, by same analysis, we see that f prime of x is decreasing, right? So that's equivalent to saying f double prime of x is negative, okay, on that interval. Again, by applying, previously increasing, decreasing test, right, on f prime of x. Okay, so by considering f prime of x as a function. So, we have the theorem we just mentioned, okay? So by just looking at the sign of f double prime of x, when f double prime of x, the sign is positive on an open interval, the graph of function is locally on that interval concave up. Negative, the sign of f double prime of x is negative. Locally, the graph of f is concave down. So, the using picture is really important, when you study mathematics, okay? And in fact, when mathematicians, they work on like a certain, like, uh, concepts, let's say, right? They don't just come up with like this type of like where, uh, polish it, like definitions or theorems, that just they are just popped out of their mind and they roll it up. No, it doesn't, right? The way they do, they examine like the different examples. Okay, they draw a lot of pictures, and then they try to see a pattern. Basically, like mathematics can be understood as like what a study of like the searching like patterns in our nature. All right. Once they find out a pattern from like examining like different pictures or like examples, then they hypothesize, right? And then they try to prove or disprove it, right? If it can be proven, then that becomes a theorem, right? So that's how the mathematicians work. Okay, right. Okay, so here comes the second derivative test. So what the theorem says is, suppose that f prime of c equals 0. In other words, c is a critical point of f. And also we assume that f double prime of x is continuous near c. Okay? In that case, if f double prime of c is positive, then f of c is a local minimum. If f double prime of c is negative, then f of c is a local maximum. How do we understand that? Actually, the very same picture I used, right, also can tell you that. Right, so here, let me go back to the picture, the crude picture I used, right? Those two pictures. So, this is where, so this is where the critical point is, okay? Right, C, right? So where f prime of C equals 0, right? C equals 0. So what's going to be sign of as you can see in this case, the graph is what from changes from decreasing to increasing at x equals c. So f of c is going to be a local minimum, but can the sign of f double prime can tell us that, right? Without actually using. I just applied actually the first derivative test, but without using the first derivative test, can the sign of f double prime of c can tell us that? Yes, of course, because the f uh, f double prime of c, in this case, what is that? The sign of f double prime of c has to be also positive here, right? Positive, because the region is concave up. The graph is concave up, so f double prime of x is positive on that interval, and x is part of that interval. C is part of that interval. So the f double prime of, in this case, so f double prime of c is positive. F, okay, f double prime of c is positive. So that's why also we need that additional condition. F double prime of x is f double prime is continuous near c. So locally around c, f double prime of c is positive. So positive means that actually on an open interval containing c locally, right? The sign of f prime of x has to be also positive. It means the graph is actually the concave up in that area, right? Concave up. And for the very same reason, right? For the very same reason, so SC, if f double prime of C is negative, then f of c is going to be a local maximum. So this picture actually tells you all of it, concavity test and the second derivative test, right? In fact, also, if you remember this picture, then even if you forget this, the statements of, say, concavity test or like the second derivative test, you can regenerate them, reproduce them, on your own. Okay, good. All right, so here's an example. Let f of x be negative x to the 4 plus 2x squared plus 2. Find the first question is find and identify all local maximum and local minimum values of f of x using the second derivative test we just studied. And second question is find the intervals on which the graph of f of x is concave up or concave down, all right? And also find all points of inflection where, so points on the graph, right, where, concavity changes, right, from concave up to down or the other way around. Okay, so we go to my notepad. So the function f of x is given by negative x to the 4 plus 2x squared plus 2, right? Plus 2. Okay, so here's step 1. Step 1, we gotta find all critical points. Okay, so for that, f prime of x, that's gonna be negative 4x cubed plus 4x, that's it, right? Okay, 2 is constant, so, it goes away. So since negative 4x is in common, I'm gonna factor it out, so negative 4x, that leaves x squared minus 2, x squared minus 1, and x squared minus 1 is factored to x plus 1 times x minus 1. And by setting this equal to 0, we get critical point, okay, critical point, x equals negative 1, 0, 1. Okay, so we get those things, right? And now step 2, so leave them there for now. And step 2, we're gonna solve the equation f double prime of x equals 0. Okay? Remember that. So f the inflection point, right? So inflection points are where like the concavity, the concavity of the graph changes from concave up to down or the other way around, down to up, right? And in fact, the sign of the f double prime of x, right? Okay, that determines like whether like the graph is concave up or down, right? Up or down, So that's why like just like in a critical point, by solving the critical points case, we solve the f prime of x equals 0, right, to find the candidates for the critical point. But in this case, the candidates for the x coordinates of the what is that, the inflection points, we have to solve the equation f double prime of x equals 0. So we take derivative once more. So here, f double prime of x, that's going to be negative 12, so we start from here. Okay, negative 12x squared plus 4. Okay, so that's going to be, I'm going to factor out negative 4. So that leaves 3x squared minus 1. Okay, or actually, you know what? Let's factor out negative 12 instead. I mean, actually, this is okay too. It doesn't matter. But I'm going to actually factor out negative 12 instead. So negative 12. So that leaves x squared minus 1/3. Okay, and then set that equal to 0. So we find the two x values, two solutions, okay? So, in this case, x is going to be plus or minus 1 over square root of 3. Okay, so those are the actual candidates. We don't know whether like one of them, or both of them, give rise to inflection point. That one can be done by considering the sign of f double prime of x, right? Just like the increasing decreasing test. So by applying the concavity test. So now step 3, I think we gathered enough information. Step 3, like I did for the first derivative test, we are going to make a table. Okay, make a table to see a whole picture of what's going on. So we are going to need again so this time the intervals we are considering are going to be determined by these points, okay? Because what we are interested in is concavity, right? Concavity, and that also concavity leads us to, the like the which critical point, gives us like a local maximum or local minimum, right? By the second derivative test. So I'll be needing 3 rows again, right? We have 2 points, right, that divides. So these 2 points divide the entire real line. So in our case, we are going to need 6 columns. Okay, we are going to need 6 columns. Okay, so first column is for x and f double prime of x and f of x. Okay, so here that's going to be, actually I'm going to use a different color. So negative 1 over square root of 3. Here, the positive 1 over square root of 3. And so this is where x is less than negative 1 over square root of 3. And here x is less than, greater than negative 1 over square root of 3 and less than 1 over square root of 3. And here is where x is greater than 1 over square root of 3. Okay, right. So now we are going to study the sign of f double prime of x, right? Sign of f double prime of x. So let's see. Okay, I pulled up. Yeah, this is actually very simple. Like this is no better than like mom's kitchen calculator, right? I'm gonna actually pull up something better. Okay, so we have 1 over square root of 3. Okay, square root of 3. So let's see. I'm just trying to get the the floating point uh, approximate. Yeah, my computer is slow. Come on. Okay, so that's negative 5.773. Okay, right. So 1 over square root of 3 is approximately, right, 0.5773. Okay, so using that value, you can use the test point, here, here, and over here also. Okay, so using that, you can easily determine the sign of f double prime of x, right? Again, you can use only like what, the one test point, okay, one test point, right? Right? So which is continuous everywhere. So using the continuity, all you have to do is to use one test point. So what happens is that the sign is negative on this interval. Of course, here f double prime of x is 0. On this interval, sign is positive, 0, and negative here again. Right. So, when f double prime of x is negative, the graph is, remember, it's concave down. So concave down, so it's frowning face, right? Positive, that's a smiley face. And then here, frowning face again. Okay, right. Okay, so we see that at x equals negative 1/3, right? At x equals negative 1 over square root of 3, right? The concavity changes from concave down to concave up. And, the x equals 1 over square root of 3, the concavity changes from concave up to down. So actually these 2 points give rise to the inflection points, points of inflection. Okay, so let us write down the points of inflection first. Points of inflection. So that's going to be, we have 2. So negative, remember again, points of inflections are the points on the graph, right? So negative square root of 3, f of negative 1 over square root of 3. Okay, so that's going to be negative 1 over square root of 3, and f of negative 1 over square root of 3, that would be 23 over 9. Okay, 23 over 9. And one more, 1 over square root of 3, and f of 1 over square root of 3. Okay, actually, the f of x, if we go back, f of x is what? X to the, the fourth power, right? And so exponents are all even numbers, 4 and 2, which means that x, positive, negative, it doesn't matter. It's going to give us the same value. So actually, the y value is going to be the same. Okay, the same. So in this case, 1 over square root of 3 and 23 over 9, the same value, right? Okay, good. And now we are going to write down the interval, okay, the intervals on which the graph is concave up or concave down. So the graph is concave down from negative infinity to negative 1 over square root of 3 union, the x, right, so, the 0 to, I'm sorry, 1 over square root of 3 to infinity. And between these two, right, the open interval, that's concave up, okay? So let's remember that. So the graph of f of x is concave down on the interval negative infinity to negative 1 over square root of 3 cup 1 over square root of 3 to infinity. Okay, so concave down. And then the graph of f of x is concave up on the interval negative square root of 3 1 over square root of 3. Okay, so the table tells us everything. And finally, right, by the second derivative test, we can also find that. Let's go back to earlier, the table. So remember, we have three critical points, right? Negative 1, 0, 1. Okay? So negative 1, uh, right. So negative 1 belongs here, okay? Because 1 over square root of 3 is approximately 0.5773. So negative 1 is, the less than negative 0.5773. So, x is equals negative 1 belongs here, right? And then, yeah, actually, you could have used like x equals negative 1 for the test point for this, right? And x equals 0 belongs here, and then x equals 1 belongs here, okay? So, here in this case, that's part of it where, like, the graph is concave up. So, f of negative 1 is going to be local maximum. F of 0 is going to be a local, the minimum value, and then f of 1 is going to be, again, a local, the what is that local maximum value, right? So we have it f of 0. Okay, so f of 0 equals 2, right? And then f of 1. No, actually f of 0 is a local yeah, f of 0 is a local minimum. Sorry, right? So this is a local minimum. And f of negative 1, so f of negative 1, uh, and f of 1, they have the same value because what? The f of x, all the exponents are, even numbers, right? Okay. So that equals 3 is a local, no, not, so two of them, local maximum values, or, local maxima. Okay, local maxima. All right, I believe, that I answered all the questions, right? So what is that? Maybe not the, exactly same order, but actually, I answered these two questions all together at the same time, okay? Right, so we found and identified all local maximum and minimum values, and also we found the intervals on which the graph of f of x is concave up or down, and then also we found all points of inflection. So we completed, right? Okay, so that's it, folks. And more details of my discussion here in this lecture can be found in my lecture note at the following address. And this is, the hyperlinked. So you just have to click on this address and it'll take you to my lecture note. And also, if you want to visit my main blogger site, just click on this word blogger, which is also hyperlinked. So, it'll take you to my main blogger site where you can find my also, other lecture notes in different subjects. Okay, all areas. All right. So thank you all for watching and listening to my lecture. Bye bye.